Let's get started on a series of examples now. For this example, we have a mass oscillating on a surface. We're going to assume that it's a smooth surface and that we have simple harmonic motion. We know that the period of the motion is 0.8 seconds and the amplitude of the motion is 10 centimeters. So it oscillates back and forth, left and right, between plus and minus 10 centimeters. At t equals 0 seconds, it is 5 centimeters to the left of equilibrium and is moving to the right. So let's make sure we understand what that means. The equilibrium position is the middle position. It's where there's no spring force. We label that x equals 0. We have, for t equals 0, it's actually 5 centimeters to the left of equilibrium. So x of t equals 0 is minus 5 centimeters. We know it's moving to the right, so we know that our initial velocity is positive, even if we don't know what the value of the velocity is. Okay, first part of the question, write the equation of motion. We start by writing the equation in symbols, and then we'll fill in what each of those symbols are. X of t is a times cosine omega t plus phi. Let's see which of those guys we know right away. A is the amplitude, that's 10 centimeters, so we're okay with that one. Omega is the angular frequency. That's not exactly given, but we can figure it out because we know that angular frequency is 2 pi divided by the period. So it's 2 pi divided by 0.8 seconds, which is 7.85 radians per second. And then the last thing we need is the phase constant, phi. Let's give that a question mark because that's not given. This is something we're going to have to figure out. How are we going to find it? Well, we don't know phi, but we do know that if t is 0, then x is minus 5. Let's put the numbers we know into our equation. So we'd like to find phi. We know that if t equals 0, x is equal to minus 5 centimeters. So that means minus 5 centimeters is equal to the amplitude. The amplitude, remember, is given. That's 10 centimeters times cosine of omega, 7.85 radians per second, times t is 0, plus the phase constant. We don't know that. We better leave that as a symbol. Okay, so 7.85 times 0 is just 0. So minus 5 centimeters equals 10 centimeters times cosine of phi. We'd like to solve for our phi, which means we'll have to get our 10 divided into the other side. So we want cosine phi on a side all by itself. So minus 5 centimeters over 10 centimeters equals cosine of phi. That means cosine of phi is equal to minus 5 over 10 minus 0.5. So then phi is equal to the inverse cosine of minus 0.500. Why don't we just pop in a note here that you have to use radians mode on your calculator. Okay, so let's put inverse cosine of minus 0.5 in our calculator and see what we get. So we grab our calculator, we set it to radians mode, and we hit inverse cosine of minus 0.5. And what we get from our calculator, we know that the inverse cosine of minus 0.500 is equal to 2.09 radians. Now, let's ask, what does this mean, and are we happy with this answer, and is this the only answer? If we think about our unit circle, cosine of negative 0.5 is somewhere over here in the second quadrant. So the cosine part is the horizontal part, and that happens, we get a cosine of minus 0.5 when the angle is 2.09 radians. So that means that the cosine of 2.09 radians is equal to minus 0.5. Is that the only answer? I would have to say, no, that's not the only answer. That's not the only angle that if we do the cosine of it, we get minus 0.5 for the answer. If we had an angle of minus 0.2909 radians, we would also get minus 0.5 for the cosine. So let's go for our math knowledge. Tells us that the inverse of cosine of minus 0.50 is equal to minus 2.09 radians. So cosine is a multi-valued function. That means there's more than one answer. So whenever you do these problems where you're solving for an inverse cosine or sine, you have to remember that there's not only one answer. Your calculator is only smart enough to get you one, but you're smarter than your calculator. You know that there's more than one. So what you have to do in these problems is write down the second answer. There's always another answer. So then you have to ask, which one is correct? They will both give the right value for position, but they won't both give the right value for velocity. So you have to test with velocity. And what we know about velocity is that at t equals 0, our oscillator is moving to the right, which tells us that our velocity is positive. Okay, so let's remember what our velocity equation is. So velocity as a function of time is minus a omega sine omega t plus phi naught. That means that our velocity at t equals 0 is minus a omega sine of phi naught. Whoops, I keep putting a naught in. There's another textbook that uses a different symbol, so there, we'll just take off that little 0. So at t equals 0, the velocity is minus a omega times sine phi. Let's try both of these values for phi and see which one gives us the correct sign for our velocity. Whichever gives the correct sign must be the correct value. So let's do our test. If our phase constant phi is equal to plus 2.09 radians, then our initial velocity, v of 0, is equal to minus a times omega times sine of plus 2.09. That's going to be a negative value. If our phi is equal to negative 2.09 radians, then v of 0 is equal to minus a omega times sine of minus 2.09. That's going to give us a positive value. Now, we know that our oscillator is initially moving right. So if velocity is negative, that means it would be moving left, so that's wrong. If it's positive, it means it's moving right, so this one is correct. Now we can finish and write our answer, our equation of motion. Our amplitude is 10 centimeters. Omega we found from doing 2 pi divided by the period, 7.85 radians per second. And now we know our phase constant phi is minus 2.09 radians. Phase constants are definitely allowed to be negative. So our position equation, position as a function of time, is 10 centimeters times cosine 7.85 times t minus 2.09. Okay, there's part A answered. Now we've got to do part B. For part B now, we'd just like to find the position and the direction of motion at t equals 2 seconds. So to find the position, we'll just plug time t equals 2 into our equation for position. So x at 2 seconds is 10 centimeters times cosine 7.85 radians per second times 2 seconds minus 2.09 radians. Put all that through the calculator, remembering to have your calculator in radians mode. You should get 5.03 centimeters. Next, for the direction of motion, what we can do is we can figure that out with the velocity. So velocity as a function of time is minus a omega sine omega t plus phi. The velocity at 2 seconds is equal to minus 10 centimeters times 7.85 radians per second, or seconds to the minus 1, times 7.85 radians per second times 2 seconds, minus 2.09 radians, and that gives us an answer of minus 67.8 centimeters per second. We've done a little bit more work than we were asked for. We found the actual velocity. What we were asked to find was the direction of motion. Our velocity is negative. That tells us that our oscillator is moving left. In this example now, we take a 350 gram mass and we hang it from a vertical spring. We see that by hanging the mass, it makes the spring stretch by 12.7 centimeters before it comes to an equilibrium. Then we push the mass gently up by 5 centimeters and we let it oscillate. If you'd like to try and visualize that, I've simulated it. It's an online simulation. So I put the mass in the spring. We see that it hangs down, it stretches the spring. And then we push it up and we let it go. So then it bounces up and down, back and forth a bit. Okay, let's see what this is going to tell us. Part A, find the spring constant. So let's think about what happens when we first hang that mass off of the spring. So our spring starts at this length, then we hang the mass on it, and it stretches down to this new length. The amount that stretches by is 12.7 centimeters. If we do a free body diagram on our mass, we know that the spring force holds it up, and the force due to gravity, or the weight, pulls down on it. This mass is at equilibrium because it says it stretches that much before coming to equilibrium. So if we write our Newton's second law, the sum of the forces is mass times acceleration. We'll have the spring force minus the weight equals 0. 0 because it's in equilibrium. Our spring force points up, so it's positive. The magnitude is k times x, where x is the amount of the stretch, 12.7 centimeters. And the force due to gravity is m times g. And that tells us that k, our spring constant, is m times g, divided by the amount the spring stretched by, 12.7 centimeters. So 0.350 kilograms times 9.81 meters per second squared, divided by 12.7 centimeters, 0.127 meters, gives us a spring constant of 27.0 newtons per meter. So there's the spring constant of that spring. The next part we'd like to find is the angular frequency of the motion. So part B. Angular frequency omega, we have two equations for that. Omega is 2 pi over t, and omega is also root k over m. You're allowed to use either of those equations. We don't know the period, so let's use omega equals root k over m. So omega is root k over m, so that's the square root of 27.0 newtons per meter divided by 0.350 kilograms. Take the square root. What we get for omega is 8.78 radians per second. You're not asked for it, but at this point you could find the period of the motion by doing 2 pi over omega, and you could find the regular frequency by doing 1 over the period. You don't have to do those things, but those are other things you could be asked for. Now part C, this is kind of interesting. Find the phase constant of the oscillation. So let's think about what do we know about this oscillation. I'm just going to play this video again. So I put the mass on, it stretches down, then I push it up. There I go, pushing it up by 5 centimeters, and then I let it go. So right off the bat, hopefully you can see that the amplitude is 5 centimeters. And that's because I push it up 5 centimeters, and release. Okay, this also might tell you the phase constant, but it might not. It's okay if it doesn't. So if I push it up by 5 centimeters, it will never go up further than 5 centimeters. It can't get up as high as 6 centimeters. It can only go back up to 5. So that's my amplitude because I pushed it up that high and then I let it go. Okay, what else do I know? At t equals 0, the oscillator is at 5 centimeters because I put it there. Okay, let's use this information in our equation. X of t equals a cosine omega t plus phi. X of t is 5 centimeters. The amplitude is 5 centimeters times cosine of omega. You can fill that in or not, doesn't really matter. 8.78 radians per second times our time of 0 plus phi. Okay, so now this whole term is gone. I'm going to divide both sides by 5. 1 equals cosine of phi. Phi is the inverse cosine of 1, remembering to put your calculator in radians mode, and that's 0. Okay, so our phase constant for this problem is equal to 0. And that's a general result. If your oscillation starts at the amplitude where it has 0 velocity, in that case, your phase constant is going to be 0. So that's just something you can remember if you wish. Okay, part D, write the equation of motion for the mass. So x of t then is equal to a times cosine omega t plus phi. A is 5 centimeters times cosine of omega, 8.78. Can put in our units if we wish, radians per second, times t plus our phase constant of 0. Okay, one more part to do. For the last section of our problem now, we'd like to find the first 2 times the oscillator has position x equals 2 centimeters. So we put the mass on, we lift it up by a little bit, lift it up by 5 centimeters, and at some point it's going to pass by 2 centimeters. What we want to know is when is it at a position of 2 centimeters. We can find this by solving the equation for position. So for part E, we know x of t equals, and this is our equation for position we wrote on our previous slide, 5 centimeters times cosine 8.78 times t. What we want to know is what is t when x equals 2. I'm going to fill in 2 centimeters here. 2 centimeters equals 5 centimeters times cosine 8.78 times t. I'm trying to solve for t, so I've got to get my cosine term on the side by itself. I'm going to divide both sides by 5. 2 centimeters divided by 5 centimeters, that's 0.4, equals cosine 8.78 times t. That then tells me that 8.78 times t is the inverse cosine of 0.4. Okay, here's where we've got to think really critically about what is the inverse cosine of 0.4. First off, got to remember that your calculator needs to be in radians mode. If your calculator is in radians mode and you do the inverse cosine of 0.4, you should get 0 or 1.16. Okay, and that's what happens when we're in the first quadrant. So your angle is 1.16 radians, and the cosine of that angle is 0.4, so we can use that and we can solve for t. 8.78 times t is equal to 1.16, so t is 1.16 divided by 8.78, and for units that's radians divided by radians per second to give us seconds for our answer, and that gives us a time of 0.132 seconds. Now this gives us one time. We weren't asked for one time, we were asked for the first 2 times. How are we going to find a second time? Well, we need to figure out what other angle can we take the cosine of to get 0.4 for our answer. So let's go back to that unit circle again. So the cosine part is this line right here, is the horizontal part. And we had a cosine, we had a result of 1.16 gave us cosine, but the angle down in the fourth quadrant also works. So it's not just the angle in the first quadrant, it's also the angle in the fourth quadrant. So inverse cosine of 0.4 can be 1.16, but it can also be 2 pi minus 1.16 to get our angle down in the fourth quadrant. And 2 pi minus 1.16 is 5.12 radians. So 8.78t equals the inverse cosine of 0.4, which can be 5.12 radians. So then t, our second time, is 5.12 over 8.78, which gives us a second time of 0.583 seconds. So that's how you can find your multiple times, is just by asking, what are my true answers to inverse cosine?